At 0121 on March 8, 2014, a Boeing 777 carrying 239 people reached waypoint Egari and its secondary surveillance transponders stopped responding. The aircraft simply dropped off the civilian grid. Later this decade, between 2026 and 2027, an autonomous robotic fleet will deploy into the southern Indian Ocean to scan a specific 15,000 square kilometer box of the seafloor. Standard tracking systems went dark at Agari. To calculate the search zone, investigators had to synthesize raw satellite metadata and oceanographic drift models. This multi-million-dollar expedition relies on a single aerodynamic assumption regarding the aircraft's final seconds in the air. When primary data is severed, investigators are forced to build a mathematical cage out of physics to reconstruct a flight's final trajectory. After the transponder went dark, Malaysian military primary radar recorded the aircraft's next movements. The plane abruptly diverted from its planned route to Beijing, executing a sharp right, followed by a tight left turn back over the Malay Peninsula, before turning northwest up the Strait of Malacca. During this diversion, the aircraft maintained a cruising altitude of flight level 340 and a steady speed of Mach 0.84, or approximately 498 knots. Simulator trials analyzed the physical kinematics required to execute these specific sharp turns. The performance data proves that the autopilot had to be manually disengaged. The cockpit was commanded by Captain Zahari Ahmad Shah, a highly experienced instructor with over 18,000 flight hours, 15 years logged on the Boeing 777. The military radar track excludes a sudden structural failure. It proves the plane was actively piloted into a radar blackout zone over the Andaman Sea. Beyond the reach of primary radar, the only remaining link to the aircraft was an automated hourly log-on interrogation signal, a digital handshake sent between the plane's satellite data unit and an Inmarsat 3 F1 geostationary satellite. This 3D Earth model defines the burst timing offset, a scalar distance measure. By calculating the delay between the expected signal arrival and the actual arrival time at the ground station in Perth, engineers could determine the distance between the satellite and the aircraft. The plane's internal clock captures the transmission time with a resolution jitter of roughly 50 microseconds. That tiny timing uncertainty translates into a margin of error on the Earth's surface, converting a precise distance into a circular band plus or minus 10 kilometers wide. These bands are known as the arcs. This equation defines the burst frequency offset, which measures the Doppler shift of the received signal. Factoring out oscillator drift and carrier frequencies reveals the aircraft's line-of-sight velocity relative to the satellite. The Inmarsat satellite was in a slightly inclined orbit, creating a distinct north-south motion. The resulting frequency translation bias provided a residual Doppler signature that matches a southern trajectory, filtering out the northern flight path. This uncalibrated metadata was never designed for navigation, yet by applying these physical models, investigators locked the aircraft into a southbound trajectory, ending somewhere along the thousands of miles long 7th arc. The 7th arc spans too much distance to search blindly. Mathematics provided the geometry, but searching an area that large requires physical constraints. Oceanographers at the CSIRO developed global circulation models to trace recovered debris back to its origin. A crucial variable in these models is windage, how the exposed shape of a floating object dictates its drift speed and angle relative to prevailing winds. In July 2015, a right-wing flaperon washed ashore on Reunion Island. Hydrodynamic testing on physical replicas revealed that its asymmetric drag caused it to drift 20 degrees to the left of the wind direction. Integrating this drift profile into global circulation models yielded a rigid negative constraint. If the plane had impacted the water north of 30 degrees south, the currents would have driven debris onto the western shores of Australia. The total absence of debris there restricted the possible impact zone to a latitude between 32 and 36 degrees south. Forensic oceanography narrowed thousands of miles of abstract mathematical geometry down to a highly specific latitudinal zone on the seafloor. At 0019 UTC, 6 hours after the initial diversion, the satellite recorded a final partial handshake. This transmission contained two anomalies, a maximum positive burst frequency offset error of approximately 13 Hz and a total lack of temperature-controlled oscillator drift. The absence of drift indicates an extremely short power interruption. As the engine starved of fuel and flamed out, the aircraft lost primary electrical power. This triggered the automatic deployment of the auxiliary power unit, which quickly rebooted the satellite data terminal. This final handshake records the absolute end of the flight, the digital gasp of a terminal system rebooting as the aircraft lost all primary power. From this point of fuel exhaustion, investigators use vertical velocity models to project the crash site. The official ATSB hypothesis states that the unpowered aircraft entered an immediate, unpiloted, high-speed dive into the ocean near the seventh arc. This model relies on structural forensic analysis. Recovered sections of the right outboard flap and flaperon show tension-induced peel failures and damage indicating they fractured while locked in a retracted, neutral position. However, an alternative theory proposes that the final frequency offset data supports an actively piloted, controlled glide. In this model, a manual descent extends the flight path significantly further east, targeting an ultra-deep depression known as the Penang Longitude Hole. Independent researchers identified low-frequency acoustic gravity waves recorded by hydrophone stations at Cape Leuven. These specific pressure signals back-project to a deep-water implosion precisely at the coordinates of the Penang Longitude Hole. The exact same digital metadata and oceanographic models yield two radically different crash sites, depending entirely on whether a human hand held the yoke during the final seconds. The upcoming Ocean Infinity seabed search carries a $70 million success fee, and all of its logistical planning relies on the ATSB's uncontrolled dive hypothesis. They will deploy fleets of autonomous marine robotics equipped with synthetic aperture sonar to map the steep volcanic ridges and deep ravines of the ocean floor. Their priority is a 15,000 square kilometer boundary known as the IG hotspot. Meanwhile, the alternative Penang Longitude Hole site sits miles outside this designated search perimeter. If this robotic armada clears the priority zone without a find, the scientific community will face a severe reckoning. They will have to accept that their mathematical cage was built around the wrong aerodynamic assumption, and the ghost flight glided far beyond the boundaries of our current models.